Hello, my name is Krzysztof Chojnowski and I am a Senior Support Engineer at SOMLabs. Today's meeting is the last one of a series of webinars dedicated to the Yocto NXP system and the SOMLabs VisionSOM modules. This time our subject is remote access via web application running on our device. Python Flask will be used as a framework for its development. We will start as usual with the preparation of the image for the necessary packages to run the server on the VisionSOM module. Next we will show you a way to connect our board to the computer via USB interface recognized on both sides as an additional network interface. And finally we will move on to the main topic of our meeting, so the web application implementation. The sources of all exercises are located in the Exercises Workshop 4 directory on the virtual machine. At the beginning, we will configure the USB interface as an Ethernet Gadget. Then we will prepare the Hello World application in Python Flask. We will use the HTML templates when creating the application. And finally, we will implement LED control and button monitoring from the browser level. To be able to run the web application, we must have a server installed. We will use the popular Apache 2 and install the Python Flask package together with it. The last package that we will add is the DHCP server, because we will configure our device as a server that after connecting to the computer will give it an IP address and allow access via both USB and regular Ethernet network. These packages are added to the package install list in the file meta-somlabs receipts FSL images FSL image validation I.MX8M append, just like on the slide. Building the image at this point would fail, as BitBake has no information from where to get the Apache 2 package. Therefore, after the standard configuration of the shell with the I.MX setup release sh command, like before each build, and after going to the build directory, we should add the meta web server layer to the conf bblayers conf file as shown on the slide. Since the bblayers conf file is generated automatically each time the I.MX setup release script is called, our entry will be deleted during the next configuration. If necessary, we can therefore add it to the mentioned script as it was described in the first part when we added the meta-somlabs layer there. We can now build and install a new version of the image on the VisionSOM device. After booting the system and connecting the device to the Ethernet network, we can verify the operation of the Apache 2 server using the browser and the IP address of the network named VisionSOM8MMCB std In the browser window, we should see the default Apache 2 HTTP server page. It is located in USR share Apache 2 default site htdocs directory on the device, so it can be changed if needed. We will now move on to configuring the USB interface as an Ethernet gadget. The most convenient way to do this is by connecting the target device to Ethernet network and logging in via SSH, leaving micro USB cable connected to the USB OTG connector after the memory programming process. Alternatively, we can connect two micro USB cables to the USB OTG and J-Link console connectors to the computer and log in via serial terminal to make required changes. After logging in, we have to manually make some modifications in the system configuration files. The changed and new files are located in the Exercises Workshop 4 Lab 1 directory of the virtual machine, so we can also copy them directly to the device. These are dhcpd-conf, so DHCP server configuration file, USB bring up, a script created by us that contains commands that start USB in the Ethernet Gadget mode, and configure the resulting USB 0 interface, and finally the USB bring up service that runs the mentioned script at boot. Let's start with configuring the DHCP server by modifying the etc dhcp dhcpd-conf file on the VisionSound device. We must provide the configuration of the subnet in which IP addresses are to be assigned by the DHCP server. Thanks to this, our server will know what pool of addresses it can use. We open the file, for example, with the nano editor and add the subnet definitions at the very end of the file as on the slide. As a result of such change, the server receives a pool of addresses from 192.168.7.2 to 700. By the way, we have to remember that the USB 0 interface must have an address from the same subnet. Before we use the USB bring-up script, which will configure the USB 0 interface, we will take a look at the commands in it. We will execute all of them manually to learn about their meaning. First, we verify the available network interfaces with IPA. Of course, the USB 0 is not yet among them. Then, with the command modeprobe g-ether, we load the module which will create a new network interface. If we have a micro USB connected to USB OTG socket, a new interface will also appear in the Linux host system, which will be automatically detected and added. After calling IPA again, we will see that the device has a new network interface named USB 0. However, it is turned off in a down state and has no IP address assigned. This address can be added with the command IP add and entering the address, remembering about the DHCP server subnet in which it must be located. This address is assigned, which we will see after calling the IPA command again. The USB 0 interface is turned off all the time. We can turn it on with the IP-link set USB 0 up command. As a result of the operation, the interface on the other side is also launched. Both sides are ready to go, but our host doesn't have any IP address yet. Instead of setting it manually, we will run the DHCP server on the device with the command system ctl start dhcpd, and after a while the IP address is assigned. We can also check the DHCP server status by calling systemctl status dhcpd. At this point, we can use the USB interface as Ethernet and, for example, log in via SSH to its IP address, or check in the browser that the Apache 2 server is also active on it. Of course, after resetting the device, we would have to repeat the entire procedure from the beginning, so we will prepare a script that will do it automatically. Let's go to the sbin directory on the device and create a USB bring-up file, writing the commands to it, just like on the slide, and remembering that the first line where the bin sh must be put for the script to be executed. Alternatively, we can copy the script directly from the virtual machine. Next, we need to enable the script execution with chmod. After launching the script, it will perform all the operations that we have just entered manually, but in order to execute it automatically at startup, we need a service that will do it for us. So let's go to the directory etc systemd system and create the USB bring up service file like on the slide, or copy it from the exercise sources on the virtual machine. This is the definition of a service that will be launched after the network configuration system service, which was defined in the after field. The script will be executed only once, which can be seen in the exec start and type set to one shot. Finally, we state that the service is used by the multi-user target unit, similarly to the previous service we created. Finally, we can start the service by calling systemctl enable USB bring up service from the command line on the device. From now on, the service will be enabled each time the system is booted and will execute the USB bring up script we created. We can verify this by restarting the device and checking if the USB 0 interface has been properly configured and whether it is active. The DHCP server should also be up and running at this point and assign an IP address to the connected host. So we learned another way to connect to the VisionSOM module, and now we will move on to creating a web application using the Python Flask framework. In the first example, we'll start with the usual hello world. The file for this application, main.py, is located in the exercises workshop 4 lab 2 directory. All exercises will be executed in the USR share SOMLabs web directory on the VisionSOM device. So now let's create this directory and copy the main.py file into it. The example is very simple, but at the same time it represents the structure of the Python Flask framework application well. First, you need to import the Flask library and create an application object. In the main part of the file, we have an uproot declaration. So this is the definition of the path under which the browser will look for the content to display. Entering a single / character corresponds to the root directory, so simply typing the address in the browser. After the browser requests content from this address, our service will respond with the string hello VisionSOM, which the browser will then display. We can now start the service by going to the directory with the main.py file that we have just created or copied and running the flask run command given on the slide. Parameter host 0000 means that the service will be available on all interfaces available in the system, including USB 0. By default, without entering this parameter, the service is available only on the local host. While the port must be added for correct redirection to our web application, in the absence of a port number, it will always be set to 5000 by default. After starting the service, let's open the browser and re-enter the device address of Ethernet or USB interface or the network name and add port 5000 to the address. As a result, we will see a page with the string given in the application, so hello VisionSOM. The error that you will probably see in the terminal means that the icon the browser is looking for is missing. and we will fix this in the next example. In the previous example, we responded to the browser with the string it then displayed. This time, however, we will modify the example to send back the HTML content in response, but with the possibility of its dynamic modification. The sources of the example are in the exercises workshop 4 lab 3 directory. We can copy it completely to USR share, overwriting the previous version. The new application consists of a main.py file just like before, but a CSS file has been added containing style definitions for this and the following examples. And of course we have also a HTML template that we will discuss in a moment. There were a few changes added to the main.py file. We imported additional functions. Send from directory, which can send a specific file in response to a browser request, and render from a template, which will create a response for us based on a HTML template. We provide the path to the templates when creating the application object. In the code, we will also find the support of the query for favicon icon, that is the icon that the browser wants to receive and which it did not receive in the previous example. We can give any icon of our own. Here we use the one provided by the I.MX8M server. The path that points to it is the argument of the function. At the end of the file, we have the support for requesting content from the root directory again. This time, instead of the usual string of characters, we will respond with the content in the HTML code. The render template function needs a template file for this and some optional parameters that will be inserted into the template. In the example, the only parameter is the system date passed to the function as a string. In the template file, we have plain HTML code with two special tags. The first is the path to the style sheet, and the second one is the place to enter the date, which is given in the render template function parameter. We can now go on to the USR share SOMLabs web directory and restart the server. We will see that the new content is in the browser, and each time the page is loaded, it will have a different date. Additionally, the content has been formatted according to the provided style sheet file. In the next exercise, we will look at the ability to control LEDs from the Python Flask application. The sources for this exercise can be found in the exercise workshop 4 lab 4 directory, so let's copy them to the Visions on Target. The file structure is the same as in the previous example, so the Py application file, style sheet, and the HTML template file. This time, however, in the application code, apart from the GET request, we will introduce a POST request service, which the browser can use to send, for example, data from the form on the page. In the Python function, first we check the type of the request. If it is a GET request, we check the status of all of the LEDs on the board and fill in the HTML template. Thanks to this, after loading the page, we can immediately provide their current status. If, however, it is a POST request, first we set the state of the LEDs according to the content of the request, and then we do the same as in the case of the GET request. Let's also check what the GET and SET LED functions look like. These are simple file operations, reading or writing brightness files of individual LEDs. The slide shows only the operation of only one LED, while the sources of the example in the exercise support, of course, all of them. Before launching the service, let's take a look at the HTML template. Its main content is a form containing 4 checkboxes and a submit button. After pressing it, the checkboxes values are sent as a post request to the server. All elements are formatted according to the attached style sheet, as in the previous example. After starting the server and reloading the browser page, we will see the form defined in the HTML file. In the displayed form, we can check the selected LEDs and use the submit button to change their status on the carrier board. In addition, we will see that after reloading the page, the current state of the LEDs is always shown in the form of active checkboxes because it is always read from brightness files by the server. In the last exercise, we will make an additional modification to implement the reverse communication. This time, instead of waiting for browser requests, the server itself will send data through the so-called server send events. The sources, as usual, have been prepared for copying to the device and are available in the Exercises Workshop 4 Lab 5 directory. The main change, according to the previous examples, is the addition of support for the stream path. As a result of the query, we return to the browser the so-called event stream, and on the server side we define a function that will send new data every time it is needed, so when it appears on the server side. In the main path, no changes, we have a generated HTML template. Let's take a look at the getMessage function, which is in fact responsible for sending data to the browser. The function opens the file dev input event0, which represents the GPIO keys device composed of 4 buttons on the carrier board, which are IO4 to IO7. This device is defined in the device tree file I.MX8M DTSI. The function, after opening the event0 file, waits for the data that will appear after pressing the button. This is a mechanism implemented by the Linux system, which we have already observed when testing the accelerometer module. After receiving the data packet from event0, it is decoded from a binary representation into arrays of values. The element number 4 corresponds to the event type, so EV key button with value 1. Element number 5 is the button code. Those on the baseboard have values from 256 to 259, assigned in the device tree. The item number 6 is the state of buttons, 1 pressed and 0 released. After receiving the event0 file is closed and the function returns the button name, which will be sent to the browser. This is where the application ends, everything else is done by the framework. Another big change happened to the template. This time it has no parameter, but a JS script is inside of it. The script subscribes itself to receive events coming from the stream path, and each time it receives data, it places it in the defined container, here the paragraph with the target container identifier. As a result, the names of the pressed buttons will appear in it. After launching the service, in the browser we will see a page with displayed names of pressed buttons. It was the last exercise that we prepared for this series of workshops about the NXP Yocto system and some labs vision, some modules. Thank you very much for the participation in this event.